What's up, Sim Scientists? It's Sim Science. I'm here. I'm not feeling too hot. So there was a shark. And I bought it. A shark pillow, I should say. And I bought it, and people's faces were on it. And then I was like, I'll put my face on it. And then I put my face on it, and now I'm sick. So I think that's why. Anyway, dynamic equilibrium. So we watched the video of the hand-face switchers, and we're talking about dynamic equilibrium. So when you have a reaction that goes both directions, a reversible reaction, you're going to get to a point where the reactions, because there's two reactions within a reversible reaction, right? The reactions are in equilibrium, and the rates are equal. And the volumes or the amounts have reached a constant. Now, that doesn't mean they're equal. That doesn't mean they're 50-50 like the video said, but the amounts are equal. When we balance a reaction, it's not always 1 to 1 to 1 to 1, or however many there are. So we're going to have different amounts when we reach equilibrium. So highlight the y-axis so that you know what these two things are talking about. And let's look at what we're looking at. So if the red line is reactance and forward rate, that's basically saying when you start. So like, let's think about the video. We started with all normal people. So however many we had, if we had 1,000 people, we started with 1,000 normal people. The rate of the forward reaction was the bigger one, and we started with 1,000 people with amount. Then as the reaction started happening, we started getting the products, which in this case was arm-face people. So they started at 0 because there were none, and then they started going more and more and more as the normal people started going less and less and less. And the forward reaction, the rate of that started dropping, and the reverse rate started increasing as there were people with faces on their hands on their faces to react with normal people, and this rate started going up, and then this goes down and this goes up until they reach equilibrium. And the amount of people, normal people, goes down until it reaches a point where it balances out, and the amount of people with arms on their faces goes up until that balances out. Okay? So amounts equals concentration. That's what this is saying. When I say amounts, we're talking about the concentration of something. So that's what dynamic equilibrium is. So now we're going to start talking about how we can adjust the way this reaction is happening. So we talked about reaction rates. Now essentially we're going to talk about reaction rates in either direction. So these factors should look similar: concentration, temperature, and pressure. Now we're going to talk about applying them to a reversible reaction. So you're going to copy this chart into your notebook. This box, this area right here doesn't need to be this big because it's just the title. So that can, of each box, that can be here. You're going to have 2 boxes here, and I'll show you those in a minute. So it's going to look like this total. You're going to want the most room here for this, the general info, and then you'll need less room for these 2 on the side. So this is what it's going to look like overall with this weird drawing, but there's one more line here and then this. Okay, and we'll get to that in a minute, so just leave those blank for now. Copy this down. Okay, so you should have it copied down. Now, the general info, like I said, this is where you need the most stuff. That just on a chart like that might not even be enough. So if you want to grab a lined piece of paper, I'll be impressed, and that would be good for your note-taking. So first of all, let's talk about concentration. So when we talk about concentration, we're talking about Le Chatelier's principle. Big name in chemistry, Le Chatelier. So basically, he was saying that if you add more of one thing to a reaction. So if we have, and you can pause this video and read this right now, that would be a good way to start this. But he's saying if you add reactant to a system, you're going to shift the equilibrium towards the products, toward the right. And if you reduce the products, you're also going to shift it to the right towards the products. So if we have a reaction, don't read that. A reaction like this. What kind of reaction is this? Hopefully you said single replacement. Basically what Le Chatelier's principle says is anything you do to this reaction in terms of concentration, the reaction is then going to react by trying to balance out again. So if I add reactants, if I increase the concentration of my reactants. Let's say I increase the concentration of AB. I add a bunch of AB to this beaker where this reaction's happening. It's going to react because there's extra AB now to react with C. It's going to shift in this direction. I'm going to have this forward reaction happening more. Okay, so I have more AB to react with C. That's all going to start reacting with all the C it can. It's going to go this way, therefore increasing the concentration of the products until it reaches equilibrium once again. Now, the opposite of that is true in that if I reduce the products, either one, both, or just one, let's say I reduce B, I may take out a bunch of B, there's less B in there now, it's again going to shift this way to compensate and try to produce more B. So the reaction is going to shift in this direction. And then it's true if I increase the products, the reaction is going to increase in this way. And if I decrease the reactants, it's going to increase in this way again. So basically, it's just always reacting to compensate for whatever you did. So let me see here if I can put into words what I remember about this from learning it that's stuck in my head. So if you have a certain amount, let's put a little a chart. If this is an axis for amount, so I have a certain amount of this and a certain amount of this. In equilibrium, they're pretty much equal. The concentrations are equal, well, the rates are equal, and the concentrations are constant. So if I take that and I change it, so let's say I really increase the amount of A, B, and C, and then this amount is smaller over here, it's going to shift to compensate for that. So it's going to shift this way to push more over this way, and then it's going to look so that it can get back to being equal. So whatever you do, it's going to shift to compensate and get back to equilibrium, adjusting after what you did. So increasing concentration of the reactants is going to shift in the forward direction. So if you increase this, it's going to shift this way to compensate. Increasing the concentration of the products is going to increase in the backwards direction. So if you increase over here, it's going to increase this way. Okay, so let's look at this example with carbon monoxide, hydrogen gas reacting to form methanol. So if we add CO2 or H2, if we increase on this side of the reaction, what's going to happen? It's going to shift this way. Therefore, after you add these things, it's going to cause an increase of the products, an increase of these, and a decrease of the reactants. So after you've added this stuff and increased this, the reaction is going to react and compensate by increasing. So the blue is you and the purple is what the reaction does. So you add this, shifts the reaction that way. It's going to increase the products and decrease the reactants to compensate for what you just did. Okay. So that's what happens if you do that. If you remove CO or H2, if you decrease the reactants, then it shifts this way to compensate for that. So if you do what's in the blue, it's going to react by increasing the reactants and decreasing the products. Okay. And then the opposite is true for the other side of the reaction. Increasing this over here is going to shift it this way, and decreasing this over here is going to do the same thing. Or we already talked about that. Sorry, I got mixed up. If we decrease this, it's going to shift this way. Okay, so basically it compensates for whatever you do. If you decrease one thing on one side, it's going to compensate by shifting towards that side. If you increase something on one side, it's going to compensate by shifting in the other direction. Okay, to try and get back to equilibrium. That's concentration. Now pressure. Let's talk about pressure. So you can take a second, pause, and read this if you'd like. So basically, when you're adjusting pressure, it's going to be affecting, it's going to either move toward or away from the side of the reaction that has more gas on it, depending on what you do. So if you increase pressure, so if the pressure increases, which means the volume decreases because Boyle's law, P1 V1 equals P2 V2. Okay, we can't forget that. Increasing one decreases the other. So think about the syringe and the marshmallows for this when you're trying to picture this. So if you increase the pressure and decrease the volume, the equilibrium is going to shift to the side of the reaction that involves fewer moles of gas. So you're taking something, so think gases exert more pressure. Gases fill the entire container. So if you have a container and it's at a certain level with gas in there, a bunch of gas particles flying around, okay, and then you take that container and you decrease the volume and increase the pressure, there's a lot less room for these gases. You're pushing them together. So it's going to shift to favor the side of the reaction that has less gas in it, because it's easier for a liquid or a solid to fit in here where it condenses than it is for gas to fit in there. Okay, so if you increase the volume of a system, volume increase and the pressure decreases, it's going to shift towards the side that has the gas, because now there's more room for the gas to fit. Okay, so we look at this reaction. I forgot to put little symbols, but this is gas, and this is liquid. Okay, so which side of this reaction has more gas on it? The left side. Both N2 and H2 are gas, so we have more moles of gas on the left side, and we don't have any gas on the right side. Okay, so if the volume of the system's changed, then the pressures of the gases are changed. So this side of the reaction is going to exert less pressure, basically, than the reactant side. So if we decrease pressure by increasing volume, what's going to happen? The equilibrium is going to shift to the left. Okay, so if there's more room inside of this container and there's less pressure, think about like a syringe. Think about a big syringe like you did for the marshmallows, and you're pulling out on the syringe and increasing the volume. There's more room for the gas to fly around, so it's going to shift towards the gas side of this reaction because the gas has room to move around. Now, if I decrease, or I'm sorry, let me finish this paragraph. Okay, so it shifts that way because you have more gas on that side, and the system is going to try to maintain the same pressure. So it wants the pressure on one side of the reaction to be equal to the pressure on the other. So that means if I increase pressure on this side, it's going to decrease pressure on this side, and vice versa. So when I do that to this reaction, I create more volume. It wants to counteract that decrease in pressure by increasing its own pressure and shifting towards the side that exerts more pressure on the container in order to try to maintain a pressure equilibrium. So if we increase pressure by decreasing volume, the equilibrium is going to shift to the right. So we increase pressure, then it's going to try and shift this way to increase pressure on this side and match it. What I said before might have been weird, now that I think about it. So basically it's counteracting whatever you do by either adding more of the gas or taking away the gas. Less gas you have, less pressure you exert. Okay, so basically it's following Boyle's law, try and maintain pressure. So in a smaller container, you shift away from the gas side of the equation, and in a larger container, you shift toward the gas side of the equation, the side with more gas. Sometimes you'll have gas on both sides, so whichever one has more gas. Okay, next factor is temperature. So this has to do with heat of reaction, which we learned about, exothermic and endothermic. So for an endothermic reaction, heat is absorbed. So heat's taken in by the reaction. So you can think of that as heat being a reactant. Heat overall is added. So you need heat plus your other reactant to get to your product. For an exothermic reaction, it's opposite. Heat's produced, it's a product. So you have your products plus heat. Okay, now as I mentioned earlier, we have a reaction. So let's say we have AB plus CD reversible, making AD plus CB. What type of reaction is this? Double displacement. Within this reaction, there are two reactions. I have AB plus CD making AD plus CB, and I also have AD plus CB making AB plus CD. Okay, so you can see these two reactions are that one reaction. I just broke it up. I took the arrows and I made them single arrows and broke that up. So when I look at this, one of these reactions in one direction is exothermic. The other reaction is endothermic. So one arrow is going to be exo and one arrow is going to be endo, depending on what the reaction is. So when we looked at exothermic, endothermic before, we were just looking at the forward reaction. But if the forward reaction is exothermic, that means that the reverse reaction is endothermic. So I say that to clarify what's being said in this box here. If you increase the temperature, you're going to shift towards the endothermic reaction. So whichever direction is toward the endothermic reaction, increasing the temperature is going to shift that way. Okay? Decreasing the temperature, you're going to shift towards the exothermic reaction. Whichever reaction is exothermic, you're going to get more of the exothermic reaction. But the simplest way to think about this is picturing heat as a reactant or product, because then you can just apply Le Chatelier's principle. So if I go back up here, in this case, in the first case here, heat is a reactant. So if I add heat, if I increase the temperature, I'm increasing the reactant side and I'm going to shift toward the products. Okay? In this case, down here, if I add heat, I'm increasing the products and I'm going to shift towards the reactants. And then the opposite is true for these as well. If I decrease heat, I'm going to shift toward the reactants in this case. Okay? So raising the temperature on an endothermic reaction, endothermic means heat is a reactant. You're adding heat to make the reaction happen. You're going to shift the system to the right. Okay, lowering the temperature for an endothermic reaction, you shift towards the left. That's what I just showed. For an exothermic reaction, heat's a product. So if you increase temperature, you're going to shift towards the reactants, toward the left. If you decrease temperature, you're going to shift towards the right. Okay, so this is the chart again. So this is saying how increase above forward reaction. So given this reaction right here, you're going to tell me how you'd increase it using a factor and how you'd increase, so that's for the forward reaction, how you would increase the reverse reaction given each factor. Okay, so this general info is where you're writing info from above. If you need to rewind the video and get more, that's fine. Or rewind it to answer these questions, obviously that's fine as well. So this is saying if I'm trying to increase the above forward reaction, if I'm trying to increase it this direction, what would I do to concentration? What would I increase the concentration of? Okay, and also to be clear, like this is saying O2, saying 2H2, 2H2O. Okay, just make sure that's clear if you wrote that down wrong. So how would I increase the forward reaction with concentration? How would I increase the reverse reaction with concentration? Increase the concentration of what? Temperature. So here's the change in enthalpy. From this you can figure out this is for the forward reaction, the change in enthalpy for the forward reaction. So when the reaction happens in this direction, I get negative 483.6. So is that endothermic or exothermic? If that's endothermic or exothermic, what's the reverse reaction? So how would adjusting temperature, how would I increase the forward reaction? How would I increase the reverse reaction? And then lastly, pressure. Look at what's gas up here. Where is there more gas? Where are there more moles of gas? On which side of the equation? Which side of the equation has more moles of gas? So how would I increase the forward reaction with pressure? How would I increase the reverse reaction with pressure? So take however long you need to answer these questions. Go back in the video if you need to, look at your notes, whatever you need to do. And then when you're done that, answer this question. This is your last question, and put a summary, blah, blah, blah. Today I learned, this week I learned blah, 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 blah. Okay, that's it for me. Hopefully I'm in the class right now. I'm not at home in bed dying because my mom's not here and I can't